好啦，時間都差唔多啦，我哋今日就開始呢個嘅講座。咁我就叫做Kenneth LEUNG，啲學生叫我做波波教授嘅嚇。我都係嚟咗呢一個Department of Chemistry 都係大概3個月左右。咁我以前咧都係響城大畢業嘅。咁今日呢個題目咧就係同我哋息息相關嘅。都係講到呢啲人工嘅化學合成物品咧，點樣會影響到野生生物同埋人類嘅健康咁樣。咁我哋今日咧就會就住呢個題目咧，就會有4個環節。咁第一個環節咧就會同大家玩個遊戲，睇下大家識唔識得點樣分辨一啲海洋生物嘅性別咁樣。跟住咧，我哋會探討一下究竟有乜嘢因素咧去決定動物嘅性別。咁第3方面咧就探討今日嘅主題啦。咁嗰啲化學合成物品點樣去影響我哋嘅荷爾蒙系統，同埋咧我哋要點樣去回應呢個問題。咁最尾咧，希望有啲時間就聽下大家發問啦。咁我就會盡量可以回答大家嘅。如果冇問題咧，我哋就可以去撇啦。好，咁問下大家究竟點樣分呢個蝦蟹嘅公乸啊？咁希望咧有人可以開咪答好嘛？俾半分鐘大家諗一諗。甚至你可以用個 chat room 回答都得嘅。如果你有答案嘅話，阿 Rachel 最早到，阿 Rachel 你有冇啲意見咧？點樣分蝦蟹嘅公乸咧？
我有聽人哋話係用個蟹嘅鉗嚟到分咯。
蟹嘅鉗去分，
係，但我唔識分。
係唔識分。咁有冇其他朋友可以有啲其他提議咧？阿蘇怡都好早到啊，蘇怡有冇答案啊？
喺佢殼嘅背面，即係個肚嗰度，因為平時買餸唔係都話要睇後面個位。係
啦，反轉去睇嗰個掩嚇。咁蝦咧，蝦又點分咧？有冇人識得分蝦公乸咧？阿 Letty 識唔識得分阿 Letty？或者 Samantha 有冇意見啊？點樣分蝦嘅公乸咧？咁 chat room 都冇人有答案。嗱，咁唔阻大家時間咧，就開估啦，不如嚇。咁咧蟹就比較容易啲嘅，反轉去咧，你會睇到嗰個掩咧，嗰個掩如果尖嘅話咧，就係雄性啦；如果圓嘅話咧，就係雌性嚇。咁但係有時候咧，如果淨係喺幼體嘅時候咧，佢就比較難啲分，因為圓同尖咧都差唔多。咁你揾隻手指揭開呢個掩咧，如果有2支白白地色透明嘅嘢飛出嚟咧，咁佢就係雄性啦。咁就可以用2個方法睇尖同圓啦，同埋揭開去睇有冇2支佢嗰個生殖器咧彈出嚟，咁就係可以 confirm 佢係公定乸。咁蝦咧就好多人都唔識得分嘅。咁蟹你會知道咧，公乸味道唔一樣啦，蝦其實都係嗰個味道唔一樣。咁呢邊咧就係個蝦頭啦，或者我用個 laser pointer 有個燈好啲。咁蝦頭位置第一對腳，如果中間再伸多對腳仔出嚟咧，呢個咧就係雄性嘅蝦嚟㗎啦。咁調翻轉，如果雌性嘅蝦咧，第一對腳咧就係冇呢一對突出嚟嘅即係雄性嘅性器官。咁反之咧，咁我喺個頭嘅下端咧，喺呢個位咧就會有一個雌性嘅佢交配嘅接合器喺度嘅。有時呢個位咧會再上少少，咁唔同品種有少少唔同。咁今日你聽完呢個講座翻去咧，屋企同朋友食飯打邊爐嘅時候咧，你就可以威下啦，即係我識得分蝦嘅公乸。實際上咧，佢唔同季節咧味道都唔一樣嘅，因為佢有啲嘅 amino acid 咧令到佢個鮮味咧唔一樣。咁如果你識得分公乸，你可以 即係去感受一下公同乸個味道嘅分別喺邊一度咁樣。希望覺得大家咧即係會覺得有趣。咁下一個難啲啦，下一個難啲就係瀨尿蝦同埋呢個嘅馬蹄蟹。咁呢兩種咧都係古時生物嚟嘅，喺化石裏邊見到嘅。咁我又想聽下大家點樣去分佢公乸啦。大家有咩意見咧？Kenneth 就頭先試咗，可以再試多次喎。朋友有冇啲意見點樣分公乸咧？咁我希望嗰個呢個嘅講座比較互動啲。
想問係咪喺上面即係綠色底幅圖係蝦嚟講？
下低呢個係馬蹄蟹，上邊嗰個咧就係瀨尿蝦。
OK，
係啦。咁你估下點樣分咧？點樣分公乸咧？試下舉一反三，即係嗰個方法咧都係同認蝦蟹咧大同小異，係咪？我哋都係反轉去睇佢嘅生殖器㗎啦。咁咧我哋又事不宜遲又開估啦。咁如果喺呢一邊你睇到瀨尿蝦咧，呢個蝦頭咧就下邊第三對腳，今次唔係第一對腳啦。第三對腳係正常嘅話咧，就係雌性。如果第三對腳咧有個小丫叉伸咗對腳仔出嚟咧，呢個咧就係佢嘅雄性嘅生殖器。咁我哋咧就可以用呢個簡單方法咧，就分到公同乸嘅瀨尿蝦。咁你下次食海鮮咧可以試下。咁馬蹄蟹咧就係一個比較特別嘅例子。咁我哋再睇翻呢幅圖咧，好多時候咧馬蹄蟹咧係一公一乸咧，即係出雙入對嘅。咁個乸咧就比較大隻啲，公咧就細隻啲咧，騎喺背脊上面。咁所以你見到咧，因為佢成日都要hold 住個 honey 咧，咁佢嗰個啲肌肉咧，即係好似我哋做 gym 咁咧，佢就會啲腳咧就變咗好粗壯。你睇下啲腳咧就變咗好粗壯。咁雄性咧啲腳咧就變到好粗壯好大隻，因為佢成日都要攬住個 honey 咧，咁就久而久之咧進化咧就變到好粗壯。咁如果女性雌性嚟講咧就好幼嘅，好苗條嘅，大家睇到。咁另外咧，因為佢要騎住嗰個異性咧，咁個雄性嘅肚腩亦都凹咗落去嘅。咁另外一個咧就好特別嘅嘢咧，就係發覺咧，你睇下咧，因為雄性要騎住個雌性啦，咁雌性後邊嗰啲刺咧，佢就慢慢地咧就一路磨咧就會係短咗嘅。咁同埋喺進化過程咧，佢都係後邊呢幾條刺咧係越嚟越短嘅。咁咧就係一個好好例子咧，即係一個夫妻咧，佢點樣去大家互相遷就愛護對方啊。雄性咧就要保護雌性，咁呢個係好特別嘅例子嚟。咁我哋落去咧比較難啲啊。咁樣點樣分八爪魚咧？八爪魚，大家諗下點分啊？Angel 有冇意見咧？或者 Zoe、Ernest 有冇意見啊？唔怕撞下都得嘅。係，大家有冇意見14位朋友 ，Angel 咧，你亦都可以喺嗰個 chat room 度打出嚟。
我都諗緊會唔會同吸盤形狀有關？
嗱，嗰個吸盤真係講得好啦，即係你呢個都諗得好聰明。咁其他聽埋有冇其他意見先？吸盤已經差唔多中咗一半㗎啦。其他朋友有冇意見？有冇意見啊 ？Ernest，唔使驚喎，即係我哋大家都去探索下呢件事。咁咧咁頭先嗰位同學都講得好啱，我睇睇先，有 chat room 有答案。佢會有人就話可能係個口部唔一樣啦， 或者係佢嗰個手個 arms 唔一樣啦。咁個 arms 唔一樣咧，係真係答啱咗嘅。咁咧就係大家可以睇下個結果啦。點解落唔到去？咁原來咧，如果我望住大家當我而家望住大家先，咁咧就係如果我係隻八爪魚，我順時針方向咧，第三隻腳咧，如果我係公嘅話咧，我前面呢段咧就冇咗吸盤嘅，就等於呢度咁啦。如果係公咧，響佢即係向前望 clockwise 第三隻腳咧，佢變咗好滑淨，冇晒啲吸盤嘅話咧，呢個就係佢嘅雄性生殖器嚟㗎啦。咁咧，如果雌性嚟講咧，就正常就係一般嘅吸盤啦。咁呢個咧就變咗佢嘅生殖器咧，就愛嚟交配。咁佢交配嘅時候咧，就將呢個第三隻即係 modify 咗嘅竹咧，就咁可以入到去雌性嗰度咧，就可以進行嗰個受精交配啦。咁呢個就係其中一個方法，我哋可以分得到啦。如果係公嘅話咧，呢個第三隻腳咧就會滑嘅。咁當然，如果我哋要睇得清楚啲咧，就做解剖啦。咁解剖咧，佢個線性咧，雄性嚟講得一條線性嘅啫，喺後邊嗰度嚟呢度。咁如果佢係雌性咧，就會有兩條嘅。咁呢個咧就比較準確啲咧，去分到佢嗰個性別啦。希望大家覺得講到呢度都有啲趣味，因為其實我哋平時食好多海鮮，見好多海洋生物咧，其實呢個咁簡單嘅一個問題，點樣分公乸咧，我哋都未必係好清楚嘅。咁喺大學裏邊咧，我哋有機會咧就探討呢啲比較基礎性嘅科學問題。咁如果有興趣再進一步了解嘅題目咧，我有個專欄叫做波哥教授演講廳喺明報嗰度嘅。咁你就只需要影低呢個 QR code，你就可以入到我專欄咧去睇下唔同相關嘅文章咁樣。好，咁而家去到第二部分咧，我哋傾一傾就係究竟性別嘅由嚟係乜嘢，係點樣樣嘅咧？乜嘢嘅因素咧去決定個性別？咁我相信大家咧對科學都有興趣咧，咁實答得啱噶啦。咁個原因咧都係因為個基因係咪？咁基因嚟講咧，如果係雌性嘅話咧，佢就有兩套嘅 X 染色體啦。如果係雄性嘅話咧，就一個 X 一個 Y 嘅染色體咁樣。咁人都係同呢個蒼蠅一樣㗎，豬都係。咁但係咧，其實成件事就唔係咁簡單嘅原來。咁原來咧基因係可以出錯嘅。試舉例啦，如果我哋正常就一個卵子就一個精子啦，咁就正常發展一個胚胎。咁亦都有啲係雙胞胎嚇，咁就二卵就有兩個唔同精子啦，咁就會係一個即係龍鳳胎啊，或者係嗰個 twin 係唔一樣嘅，因為佢有兩個唔同精子啊。咁另外一種情況咧就係一個卵子兩個精子，而係咧係同一個體咧佢發展，咁就可能變到呢隻龍蝦咁啦。亦都有啲情況咧，佢變咗嗰啲基因係 Mosaic 發展咧，就係唔係話咁樣平均分，係響成個體咧佢混亂地發展都會有嘅。咁除此之外咧，我哋發覺就係嗰個嘅 chromosome 可以有增減嘅，會多咗一條染色體或者少咗一條染色體咧，都影響到佢性別特徵嘅。咁其他咧就係啲基因去改變啦，即係唔同嘅時候咧，亦都影響到個荷爾蒙嗰個嘅功能啦，同埋佢嗰個 metabolism。咁第三方面咧就係一個表基因嘅問題。咁我而家咧就探討一下。首先俾你睇一睇一個個案咧，就係話原來咧好多人咧都會有呢個病嘅，呢個嘅基因出錯咧就係本身呢個應該係一個基因欄嚟嘅，佢有一條 X 一條 Y， 但係咧好唔好彩咧，佢就多咗一條 X 出嚟。咁呢個嘅病咧就係 XXY 病，即係叫做柯林菲特氏症。咁呢個症狀係點咧？就係佢個表徵睇嚟咧都係一個雄性嚟嘅，但係咧佢裏邊咧就有好多機制咧都發展為一個好似雌性咁樣。 咁因此咧呢一個嘅人咧就係雌雄同體，咁佢就不育啦，同埋咧佢會有陽具同睾丸，但係都係縮細嘅形式出現啊。咁呢啲嘅情況咧其實好普遍嘅，喺全球嚟講咧係 1 in 1000，即係1000人咧就有一個咁嘅例子。咁所以喺人類當中咧，雌雄同體咧係一個幾普遍嘅現象嚟嘅。咁另外一個值得探討嘅問題咧就係呢個叫表觀遺傳學嘅一個重要嘅一個環節。我哋其實要問一個問題咧，就係關於基因咧，佢會唔會打印出嚟變咗啲蛋白質啊？因為咧，如果你攞我一條頭髮去做基因排序啦，同時間咧你又攞我一塊指甲去做基因排序啦，咁其實排出嚟一模一樣嘅，都係嗰個即係我哋叫nuclear DNA， 都係喺個細胞核裏邊嘅遺傳出嚟嘅 DNA 個 sequence 一模一樣。咁你問下點解唔會喺個手指甲生啲毛出嚟，生啲頭髮出嚟咧？咁原來咧喺嗰個由個 DNA 去到 RNA 再去到蛋白質咧，喺呢一個嘅印嘅過程咧係會受其他嘅機制咧去影響嘅。咁呢啲機制咧就係喺嗰個我哋遺傳落嚟個基因以外嘅一啲嘅機理嚟嘅，咁都統稱為一個叫表觀遺傳學。咁啊舉一個例啦，就係如果我哋要印一段嘅 DNA 去印做蛋白質，咁首先咧就喺嗰個呢個 chromosome 嗰度，我要 unwind 即係整翻散去。咁啊整咗個 DNA 出嚟咧，我哋就可以印某一段。咁我亦都可以唔印某一段，咁你要去取決啦。咁我哋咧就係淨係指甲位咧就係印翻指甲嗰段。咁唔印嗰啲咧，我哋就會黐一啲嘅化學物質上去。咁呢一個咧就係 methyl group CH3，咁啊黐咗上去嗰個基因上邊咧，就可以令到佢唔印。咁其實仲有成10多20種嘅機理咧，令到印同唔印嘅，包括一啲好短嘅 RNA 咧，佢都可以我嚟黐上去咧，令到基因印或者唔印啊。咁你話咁呢個機理點同呢個性別有關係咧？咁啊舉一個例子嗱，正常嚟講咧，如果呢隻老鼠咧，佢媽咪生完 BB 咧，佢就會去幫 BB 清潔啦，同埋會餵奶咁樣嘅啊，跟住咧就會食翻嗰個胚胎嘅，咁啊去補充營養咁樣。咁喺呢個例子咧，就係佢咧就一邊嘅基因由嗰個爸爸嚟，一個媽咪嚟，咁啊兩個基因咧都會係話俾你聽咧，你係一個好中意打鬥嘅雄性老鼠嚟嘅。喺大自然嚟講，見到呢個情況，因為佢係媽咪嚟嘅，咁佢就會揞住唔俾佢印嘅。咁呢個咧就叫imprinting嘅epigenetic mechanism 咧，就話唔俾佢印。咁咧就佢會有一個機理咧去控制住佢。咁如果你將呢個機理掹走咧，佢就會印出嚟。就正如呢隻老鼠咧，佢生完 BB 就走鬼咗啦，係好似一隻公嘅 behavior。咁啊喺呢個實驗話俾大家聽咧，就話有時候都唔係喺基因嗰度出錯，而係喺嗰個呢個叫表觀基因，即係印唔印嗰個基因去到蛋白質出錯咧，咁都會影響到嗰個生物嗰個即係佢嗰個 social behavior 嘅。咁呢啲咧都係非常之有趣嘅科學嚟嘅。咁可能大家都有睇書會知道咧，即係原來控制性別都有好多嘅因素，譬如喺呢啲爬蟲類啦、龜啦、鱷魚啦，原來溫度咧就可以控制佢性別嘅。咁佢哋咧每一隻嘅動物，即係呢啲爬蟲類咧，佢已經有咗雌雄嘅基因喺裏邊。咁佢點樣印唔印係雌一定印做雄性咧，就佢取決於嗰個溫度啦。譬如呢隻沙漠龜咧，喺低溫嘅時候咧，喺低溫23度嘅時候咧，就全部都係雌性。咁啊，到中溫嘅時候咧，就大部分70%咧都係雄性。咁啊，再高溫咧又全部變翻雌性。咁我哋喺海灘見到啲海龜啦，或者啲陸龜咧，就多數係喺高溫嘅時候咧，就 響低溫嘅時候咧就全部係雄性嘅，響高溫嘅時候咧就全部雌性。咁你諗下喺海灘咧嗰隻海龜刮個窿咧，咁佢生啲蛋啊。咁上邊受熱多啲咧就會全部雌性啦，下低咧就會雄性啊。咁另外一種嘅機制咧就係、是、如果有營養嘅時候咧，佢嗰啲 BB 咧就大部分係需要多啲營養嘅。譬如呢隻海鷗咧，佢雄性係大隻好多嘅，要食好多嘢。咁當魚葉嗰個魚獲好豐富嘅時候咧，佢哋先會生多啲嘅雄性嘅。但係如果喺魚獲好差嘅年份咧，佢哋大部分咧就生雌性，因為嗰啲雌性就食少啲嘢嘅，細隻啲嘅。咁另外咧，魚就好特別嘅，魚咧就有好多種唔同系統，有啲一出生咧已經有公同乸之分，有啲一出生咧佢係雌性，後期就變做公，又或者調翻轉一出生係公，後期咧就變做乸咁樣。咁舉例咧，呢石斑魚一出世咧就係雌性嚟嘅，咁咧就喺佢群落裏邊最大嗰條雌性咧就會變做公嚇，咁咧佢哋就可以繁衍啦。咁如果隻公俾人調走咗，唔見咗啦，咁佢剩翻落嚟最大嗰隻乸又會變翻做雄性嘅，呢個係一個好特別嘅系統嚟。我哋叫做佢係比較plastic，即係嗰個變數彈性好大嘅。咁另外咧就係荷爾蒙，咁荷爾蒙咧就係我哋今日個主題啦。我都講得好慢，因為啲時間都過得好快。咁咧呢個就係貓個媽咪個肚啦。譬如呢隻係一隻基因公嚟嘅，呢兩隻係基因乸。咁如果呢兩隻基因乸咧，佢生得好快咧，佢荷爾蒙可以分泌出嚟咧，就影響咗你個基因嘅雄性嘅貓。咁到佢成長嘅時候咧，佢就受咗雌性荷爾蒙咧，就出咗嚟咧係一隻貓女咁嘅。但係實質上咧，佢體內咧係有睾丸嘅，係一隻雌雄同體。咁呢啲喺大自然裏邊咧都係常見嘅現象。咁喺人嗰度啦，你見呢個男士咧，佢就每日去食呢啲嘅女性嘅荷爾蒙咧，咁佢就會越嚟越似女性啦，亦都長出女性嘅身段咁樣。咁呢個都係大家好清楚。咁原來咧，我哋用嘅生活上邊嘅化學劑咧，好多時候咧都係有啲化學物品咧，同我哋荷爾蒙嗰個化學結構差唔多啊。咁佢就可以做到咧，好似真係荷爾蒙嘅功能啦。佢去咗荷爾蒙嗰個受體咧，就產生咗作用，就等於咧插頭同個插座一樣，咁去通電啊。咁有情況咧就係佢冇兩隻腳正負電極，得一個嘅啫。咁佢插咗落去個插頭咧就唔着電，但係咧佢就封咗個位咧，就其他荷爾蒙就入唔到去咧。咁就我哋就抑制咗其他荷爾蒙嘅運作咁樣。咁呢度就舉咗個例咧，就係呢啲係天然嘅雌性激素咧。咁就係一個苯就加一個 OH。咁咧呢個咧就係天然嘅。雄性激素咧就係一個苯就加 double bond O 咁樣，咁呢個係人工合成嘅雌性激素咧，咁你會睇到啊嗰個形態咧就同天然咧係一樣啦，有呢個嘅 benzene 加一個 OH 咁樣，咁呢個咧就係常用嘅DDT 殺蟲劑，咁佢嗰個結構咧差唔多，咁佢就會有個chlorine喺度啦，但係喺鹼性情況咧就會係可以變翻 OH。咁因此咧 ，DDT 咧都係有呢個雌性激素嘅作用。咁好唔好彩咧？我哋嘅水域咧就大部分嘅海魚咧都有呢個 DDT 喺嗰度。咁我哋其實體內咧都食唔少呢啲咁嘅污染物。咁 DDT 咧就係喺80年代已經禁用啦，但係喺60年代到80年代咧就影響好多雀仔咧，佢哋就不育咧，甚至到咧係絕種嘅。咁點解咧 ？DDT 落咗嗰個食物鏈咧，佢就隨住食物鏈咧擴大，咁就嗰個劑量就好高啦。咁咧當個 DDT 劑量越高咧，個媽咪生咗啲蛋咧，個蛋就越嚟越薄，個殼越嚟越薄。咁個媽咪一坐上去孵化嘅時候，咁就死咗啦。咁所以咧嗰個群落咧就越嚟越少，咁直至到80年代中開始禁用咧，咁啲雀仔咧先翻嚟。咁人有啲咩影響咧？咁喺 東南亞地方啦，例如印度啊同埋柬埔寨咧，法國嗰個地方咧都成日用 DDT。咁嗰啲嘅少女咧就發覺係好早熟啦，8歲已經長出乳房啦，10歲就有月經。咁呢個就因為 DDT 佢會影響佢哋嗰個荷爾蒙系統啦。咁至於香港咧，其實我哋做過研究發現咧，我哋嗰啲污水排放出嚟啦，即係因為嗰個污水廠咧就唔可以除晒污染物嘅。咁排出嚟咧，佢就有12種啦，裏邊咧包括咗7種咧都係雌性荷爾蒙嘅EDC，即係呢啲咁嘅干擾素嚟。咁包括最多咧就係浪納菲諾。咁呢個咧就係從我哋用洗手液出嚟咧，佢嗰啲分解物嚟嘅。另外一個咧就係塑化劑 bisphenol A， 咁呢個咧都係好高嘅。咁落咗河流海咧，咁會影響到嗰啲生物啦。咁例如咧就會令到啲雄性嘅魚咧雌性化，會揾到睾丸佢哋會有精子，亦都有卵子喺條魚度嘅。最嚴重咧，佢哋又會不育嘅嚇。咁我哋日常用好多嘅膠咯，啲塑化劑咧常聽就係雙酚 A 啦，BPA、bisphenol A。好多人都知道佢有問題㗎啦，會影響到荷爾蒙系統，所以啲公司咧就將佢取締咗咧，就其他嘅化物品就 bisphenol F 同埋 bisphenol S， 仲有好多其他嘅。咁所以咧聽到話 BPA3 咧就唔好咁開心住，因為佢取締咗嗰啲化物品咧，唔一定係安全嘅，因為都係有呢個 benzene OH group 喺嗰度嘅，一樣會影響到嗰個荷爾蒙系統嘅。咁所以盡量咧都少用塑膠或者塑膠包裝嘅食品。咁另外一個咧就係我哋常常去買嘢嘅時候咧都會有啲發票啊。咁原來啲發票咧裏邊所含嗰個bisphenol S 或者 bisphenol A 嘅量係非常之高嘅。咁可以高到咧就係3000到12000個 ppm。喺台灣做嗰個測試咧，80%嘅呢啲發票咧都有含有啲高劑量，所以出完街咧摸個發票咧，記住洗手先好食嘢啦。咁有啲咩問題咧？咁就會增加致癌嘅風險啦。發覺就係喺一啲前列腺癌病人身體咧就發覺高劑量嘅呢啲 bisphenol A， 咁同埋咧亦都會影響到發育嘅。如果 bisphenol A 喺體內高嘅話咧，就會令到啲小朋友容易超重啦。除咗我頭先所講嗰啲嘅污染物咧，我哋成日都用嘅另外一種嘅phthalate 呢一種嘅塑化劑咧，亦都係好普遍喺我哋日常食用嘅物品裏邊咧發現嘅。咁台灣就曾經出過事咧。好多研究發覺咧，就會影響到男仔嘅發育啦，陰莖變短啦，睾丸唔發育啦等等啦，亦都令到咧雌性嘅少女咧就會提早發育啊等等。咁其實我哋而家咧就發覺呢啲污染物咧就無處不在嘅。唯一辦法咧就係減少食呢啲包裝食品同埋飲料盡量咧即係少啲接觸膠嘅物品咧就比較安全啲。咁我哋作為科學家咧，可以做咩咧？就話可唔可以用少啲呢一啲嘅 EDC 喺產品上邊，仍然發揮佢嗰個功能。再重新設計嗰啲化學嘅物質，令到容易啲分解同埋減低嘅毒性啦。可唔可以揾一啲替代品咁就係唔會造成呢啲禍害嘅。另外一方面喺污水場裏邊，可唔可以將佢哋拎走咧？咁呢啲都係我哋嘅相關研究。咁希望咧，如果你有興趣呢個題目咧，將來你嚟到城大讀書嘅話咧，可以嚟到我哋嘅國家重點實驗室，我哋呢個就係海洋污染國家重點實驗室咧，可以嚟做實驗啦，可以解決更多呢一啲嘅 EDC 嘅問題。咁如果你有時間留低咧，可以繼續發問。咁我就講到呢一度啦。大家可以隨便發問，或者用嗰個 chat room 都得。 頭先有位同學問啦，好想問嗰個 XXY 嗰個病係有什麼 factor 影響最大？咁呢一個就會因人而異嘅。咁多數咧嗰個響 BB 咧發現咧，佢可能即係個表徵咧仍然係一個雄性啦，即係但係佢可能嗰個陽具會比較細啦，或者睾丸又比較細，有時候甚至到佢個睾丸冇 descend 冇跌到落嗰個陰囊嗰度。咁有時候咧有啲以前嘅做法咧，佢哋有啲例子就係佢亦都有陰道同時間。咁變咗以前咧唔係知道咁多嘅時候咧，就有啲醫生就做錯咗，就可能將嗰個陰莖切除咧，就當佢係雌性 baby。咁其實有啲 documentary 即係紀錄片咧就講呢個議題嘅。咁喺歐美咧就形成都好多法律責任嘅問題咁樣。咁至於佢成長咗影響最大咩咧？就係佢不育咯，因為佢本身佢多咗 X 咧，咁佢就會影響到佢自雌性。但係實際上佢有 Y 嗰個 chromosome控制住咧，佢係基因男，但係實際咧佢又做唔到一個男士嗰個 function， 即係譬如話係製造一啲足夠嘅有活力嘅精子咧，可能就做唔到。咁因此咧就影響到嗰個嘅佢嘅生育能力啊。咁呢個就係最明顯嘅影響。咁睇下其他朋友有咩問題先。大家有冇問題？其他同學你可以用嗰個 chat room 講都得嘅。
有個問題想問。
你大聲少少嘛，唔該。
係，我話有個問題想問，咁就係有關於其實 F 科係當係 chemistry 啊，定係當佢係 bio？因為我見好多時候就係即係點講，我唔清楚呢一科係究竟要點樣分。
呢一科咧就屬於我哋叫 environmental pollution 啦，或者係environmental toxicology。咁就響我哋嗰個化學課程裏邊嘅其中一個選科嚟啦。咁你就都要好了解化學嗰啲物質嘅結構啦。咁同埋咧，我哋都要教你點去測度呢啲嘅化學污染物嘅。咁至於毒理嗰方面咧，就會教你點樣去做一啲分子生物學嘅方法去測試啦，或者用一啲唔同嘅小型嘅動物咧去做測試咁等等。咁最終我哋都想去解答嗰幾個問題，即係第一，譬如話頭先講啲雙酚 A 污染係咪好嚴重？人體接觸量有幾多？咁嗰個接觸幾多先會影響到個人體健康或者嘅動物嘅健康？咁呢啲咧都需要去做一啲化學分析嘅咁樣。咁所以環環緊扣啦。即係我哋而家化學咧都慢慢係越嚟越多涉及到chemical biology， 因為其實人體裏邊嗰啲 DNA 結構啦，咁都係化學嘅一部分嚟。咁希望呢個答案清楚嘛？係
明白。咁但係因為我自己喺中學入面咧，我就我嘅即係我係修讀 Chem Bio 嘅，但係咧。但係因為我自己嗰個 chemistry 就嗰個成績唔係好好咁樣，因為都唔係好跟得到。咁但係反而 bio 我覺得就係比較多係背嘢嗰方面啦。咁而且嗰個成績都還可以嘅。咁我想問，其實有冇即係我係都會想，如果可以讀到呢一科都會想讀嘅。咁可能有冇咩建議可以即係令到我即係？如果即係起碼可以幫到我喺 chemistry。
其實咧我哋亦都有另外一個嘅部門咧，就係 biomedical science。咁其實喺嗰邊嘅學生咧都可以修讀我哋呢一邊一啲選科嘅咁樣。咁嗰邊就係比較 以 biology 為重一啲嘅。
係，明白。但我真係比較想讀有關於環境嘅嘢多啲。
咁你有幾個途徑咧？即係除咗係可以喺elective 嗰啲 courses 裏邊 take 咧，咁亦都可以將來讀個master program 或者甚至到 PhD program 咧，係去進一步去進修嘅，都可以。
係，好啊，好啊，唔該晒。
咁其他同學仲有冇啲問題？最後機會，大家有冇問題想問？最尾問下大家，你覺得呢個咁短嘅 talk 有冇趣味咧？起碼你識得分下一啲海產嘅性別係嘛？亦都了解到我哋而家其實嗰個生活嚟講都接觸到好多對我哋有影響嘅污染物。咁記住掂完嗰啲發票咧，就要洗手先好進食啦。咁我唔知大家覺得 O 唔 OK 係？如果 OK 你就喺個 chat room 俾個 like 我啦，等我知道大家嗰個嘅感覺點樣，好嘛？係多謝。咁如果冇問題嘅話咧，咁就唔阻大家去聽其他嘅講座。咁如果有需要有問題咧，亦都可以電郵俾我嘅電郵我就寫咗度啦KMY LEUNG 咁後邊都係CityU 常用嗰個嘅電郵咁就多謝各位，好啦，拜拜。
Welcome to the public lecture organized by Department of Chemistry of CityU. So for the people who are not in Hong Kong, welcome to this virtual space of Hong Kong. So today is a great day. We have a lecture by one of our professors in the department, live stream from France. So, we have also here Professor Alex Zhang, the prefect of our university, and he will now introduce our speaker today. Professor Zhang.
Okay, thank you, Yunhua. Good afternoon, Professor Jean-Marie LEUNG, colleagues, fellow teachers, and students. Ladies and gentlemen, on behalf of the City University of Hong Kong, it's my great pleasure to warmly welcome you to this live lecture by Professor Jean-Marie LEUNG, co-organized by Office of Provost, College of Science, and the Department of Chemistry. Today, we are very delighted to have more than 200 participants, particularly 150 secondary school students and teachers join from their home, schools, offices, and anywhere. There are also some friends watching on YouTube, where we do the live streaming. Thank you all for supporting this event, and hope that you will enjoy it this afternoon. This is such an extraordinary time that COVID-19 pandemic has confined half of the world population to self-isolation, confronting the worst economical prospect since the Second World War. Many people are losing hope and becoming cynical, and also cynical of the bleak and also uncertain future. Chemists' minds are not exactly the same. We know that the universe is built from only 118 chemical elements. The combination of this element can give us the deadliest virus, okay, but can also give us the most miraculous cure, to instill hope to our friends, and to celebrate the importance of chemical science in this precarious time. We are most honored to have invited Professor Jean-Marie LEUNG, our distinguished visiting professor and the Nobel Prize winner in chemistry 1987, to give us a special gift, a live lecture from France. Professor Lan is currently professor of the Institute of Advanced Study of the University of Strasbourg, senior fellow of the CityU Institute for Advanced Study, and the visiting distinguished professor of our Department of Chemistry. Prior to his tenure at Strasbourg, Professor Lan has been faculty member at the University Louis Pasteur, then the College of France, over the past 3 decades. He was awarded the Nobel Prize in Chemistry in 1987 for his studies on the chemical basis of a molecular recognition, which also plays a fundamental role in biological processes. He furthered his effort in launching the now flourishing field of supramolecular chemistry. Today, the topic of Professor Lan's lecture is Steps Toward Life, Chemistry. He will share his philosophical view in chemistry, looking at how the evolution of the universe has generated more complex form of matter through self-organization from particles up to living and a thinking organism, and in particular, what chemistry has been taking part during the process. I trust his sharing will definitely bring lots of insights. So without further ado, please join me in welcoming Professor Lan. Professor Lan, now the platform is yours.
Thank you very much. You hear me clearly?
Yes.
Good. So it's a pleasure to be virtually in Hong Kong. Unfortunately, I would prefer to be there really and not virtually. But these are the times where we connect virtually. I would like to thank the Department of Chemistry for organizing this lecture. And I think the slight delay in the lecture, this is just nothing. No reason to be worried about. Half an hour is nothing if we look at a lifetime, if we look at the age of the universe. So let's forget that. I'm happy to be back here virtually, as I said, at City University, where I am a member of the chemistry department, at the visiting professor, and also at the Institute for Advanced Study. It's always a pleasure to be in touch. Let's say you mentioned, Professor Jen mentioned that they are very unusual times, which is true. It is true, they are very unusual, but not just because there is a virus running around, also because our conditions, the way we have developed, the very advanced state of our societies has made it also sensitive to perturbations. These perturbations are probably very minor. Of course, for the moment, we feel them very strongly, but this is just passing. And if you look back into the past, when there were the epidemics of plague, many, many more people got killed. And it took for years and years and years and was coming back every 10 years. So let's calm down and consider that we are living a perturbed time, but this time will recede. And as one says, after the storm, the sun shines. We are in the hands of science, and all this big talk we have all over the world coming about solutions and this and that. The solution is in the hands of science. We need a drug, we need a vaccine, and then things will be normal again. So let's just wait until we have that. It may take some time. And of course, we are all impatient. We all want to go very quickly. We all want to have our way of life. But all right, sometimes that is not so easy. And we have just to wait it out until the solution is found. On the scale of centuries, this is just a very small perturbation. Of course, it touches many people, and for them, it's not necessarily a small perturbation, but it's a local perturbation. So I will come back to these things, and maybe there will be questions about also these general questions, this general problem. Let me come then to my talk. I sort of consider it as a sort of a chemical journey, starting very early and coming now to the state in which we are. So the title is Steps Towards Life, and the answer to these steps, they'll deal with chemistry, and I will try to show you. Of course, you will see also that it's not just chemistry, but chemistry plays a very important role there. In order to put everything into perspective, let's start a very long time ago, 14 billion years. At that time, there was a Big Bang. And out of this Big Bang, our universe was born. At the beginning, as you can see here, this red spot I show you, the universe expanded very quickly. At that time, it was very, very hot. It cooled down rather rapidly, but it was still very hot after 3 minutes. After 300,000 years, it was about 6,000 degrees. At that time, at these early times, there was no chemistry. It was much too hot for that. This was what you may call the age of physics. No chemistry. But the universe cooled down, and it became cool enough to have particles form and particles associated together to give atoms. And then atoms could combine to make constructions which we call molecules. At that time, about here, chemistry started in our universe. The bricks of matter were formed, which we call elements. I will come back to that. And chemistry started. These objects which formed became bigger by random combinations. They began to associate. They created at some stage sort of separations, membranes, and so on. And out of that, something new, very new appeared, a property which we call life. Around here, on our planet Earth, life started there. This is the age of biology. But at least on our planet, and I'm quite convinced on others too, evolution continued. The biological organisms became more and more complicated. They evolved. They developed other features, other properties, and the most important one by far is thought, thinking. These are the steps towards life and thought. It is because of thinking that we are here together, that we talk to each other, that we are able to be together today. Thought is represented here by this sculpture, by a French sculptor called Auguste Rodin. As you see, it's a person sitting on a rock and thinking hard. It's called The Thinker, this sculpture by Rodin. Let me also already now insist on one thing. As you see on the right, that's the end of the screen, but it is not the end of the universe evolution. Our universe will continue to evolve. Nothing can stop it. And if we hear people now on the planet Earth, our point in space and in time, we have to be modest. We are just a point in space and in time. This will continue to evolve. Nobody can stop it. And if we don't take advantage of what we can do ourselves, we will be just the slaves of this evolution. But we have to take it in our own hands. I will come back to that later. So the question then is, how does this universe evolve? This looks like a black screen with nothing on it. Indeed, there is nothing on it. But what I want to show is this. Our universe is made up, as our cosmologists tell us today, of about 95% of darkness, 68% of dark energy, 27% of dark matter, which means 95% which is dark and we don't know much about. However, there is 5% visible matter. And this visible matter, this is what we are part of, our visible matter. And that is the matter that matters, as I like to say. This is the matter which is important for us, because we, as human beings, on a small ball in the universe, the planet Earth, are part of that visible matter, like the Earth, like the moon, like the sun, and so on. And this makes up just 5%, but it is the important matter, the matter that matters. Now, the evolution of this matter has been an increase in complexity, and let's say information, complexity and information as a function of time. Initially, the matter was divided, split into particles. Then it became condensed, making assemblies of particles, and then became organized, making entities, material entities, which had a certain organization. At some stage, it became living by a process we don't understand yet. We don't know the details, but we will know more and more about it. And in the future, we'll understand in detail what has happened and how it happened. Then it began thinking, which is a big, big step. Between living and thinking matter, I consider that the step is much more important than between organized and living. Because without thinking, we would not be here. Life would have been no interest if you don't think. Beyond that, there may be something else. We don't know what it is, but we cannot exclude there is something more complex, more informed than what we know as thinking is for us. So that is the evolution of matter under a sort of a force, which is like a pressure of complexity and information towards complex forms of matter. At this point, we now have to ask a big question. What is the big question we have to ask? This question is, how does matter become complex? What are the pathways by which we can go from the elementary particle to a thinking organism? And maybe there are even higher forms of complex matter, which could be evolved or created. We don't know that. Maybe. So, what is the answer to that question? In order to try to get an answer, to find an answer to this complexification, this arising of more and more complex forms of matter, mankind on our planet, in this very, very small spot in the universe, in small spot in time, small spot in space, mankind created something we call science. And I am going to consider just 3 areas of science which in some ways form the basis. Physics deals with the laws of the universe, the way our universe functions, the way things develop, the way things in our universe interact, how it has formed, how it develops, and so on. These are the laws on which the overall universe depends. Biology is another part of our science on our planet. Biology deals with the rules of life. These are rules, they're not laws, because the laws are the basic laws which are those of our universe. But these are the rules of life. How does it work? Now, what is chemistry doing? Chemistry is trying to build this bridge between these general laws of physics and the rules of complex matter, that means life, thinking, and so on. It builds the bridge towards complex matter. How is it possible, is the question. How is it possible to go from general laws, the laws of our universe, to specific expressions of these laws, which have generated, which have given rise to an organism like mankind, like human beings on our planet? Now, one may give an answer to that question by one word. Now, this seems to be very strange. How can one just give an answer in such a complex, in just something we don't know yet. It's just that there is a process which I consider is the answer to that, which is self-organization. That doesn't mean anything and means everything. It's a word. We understand the word. It means that it has happened by itself, by its internal structure, has led to this development. And self-organization is the basis of the arising of complex matter in the universe. The self-organization is a process which we have to try to understand, which is at the basis of generating living and thinking organisms. Now, one can even say that it is a cosmic imperative in our universe. Our universe has such a structure that it will self-organize, it will lead to complex matter somewhere around in the universe. This self-organization, can we say a little bit more about it? We can talk about self-organization on the cosmic, on the universe scale, on the large scale of the universe, which occurs through gravitational forces. Cosmologists tell us that the structuration of the universe is the result of these gravitational forces acting on the initial inhomogeneities in density of matter after the Big Bang and the rates of expansion at very early times. This led then to the generation of the objects present in our universe. But that is not what we are concerned about, so to say. Why we are interested in this complex visible matter, this 5% complex matter, which is the molecular matter, we come back to that later, and this has been generated through electromagnetic forces acting on the pieces, the building blocks of visible matter, of matter. And these have led to sort of structuration by random combinations. Random meaning that there was no design in it. It was just the laws of our universe which lead to the formation of these molecular matter entities, these combinations of structures of elements of the universe. Now, let's go back just to think about this evolution. You know all that living organisms on our planet evolve through what is called the Darwinian evolution. But before there was any life, there could not be a Darwinian evolution. Therefore, there was a prebiotic, purely chemical evolution, which was the self-organization of non-living matter preceding the self-organization and the evolution of living matter. And this is a much broader evolution than Darwinian, and even Darwinian evolution may be considered as a chemical evolution because the basis of it, as you will see later, is residing in the genome of living organisms. So chemistry is usually considered as the science of the structure of matter, how it is built, and the transformation of matter, how matter can be transformed, how the entities of matter can be transformed into one another. This again, we will consider more clearly in a moment. Now, people have a long time ago started to ask themselves questions. Mankind tried to see, what is this? What are we made of? What is around us? What does it mean? And there were 2,500 years ago, in a small country called Greece in Europe, there were people who were thinking about, and probably in other regions of the world, there must also have been. And one of them, one of those so-called philosophers, Empedocles, proposed that matter was made of elements, earth, fire, air, and water, 4 of them, which by combination give properties. Fire and air was hot, air and water was humid, cold for earth water, and earth and fire was dry. This was an attempt, it was already a proposal, it was simple and we could consider it trivial, but okay, it's a start. It happened, however, that at the same time, there was another person who had a much, much deeper insight into that. Without going to the details of the history of science, nevertheless, there is somebody called Democritus, who at that time had a much deeper insight. He considered that matter is particulate. It is made of very small particles, particles which cannot be divided anymore. And in Greek language, atomos means you cannot cleave it anymore. Atomos is atoms. So this term of atoms was introduced as atomos in the Greek language, and Democritus was the person, one of them at that time, there were many developments, who proposed that. Now, it is said that not only this looks like a theory, a proposal, a philosophical proposal, which it may well be, but we can also say that, and people think that Democritus had a deeper insight. And let me just show you how you could convince anybody in the street that matter must be particulate. Take a glass of water, take a piece of sugar, put the piece of sugar in the glass of water. The piece of sugar dissolves. The piece of sugar disappears in the glass of water. If matter had been continuous, this would not be possible. The piece of sugar could not enter intimately into the water. Therefore, matter must be made of particles which can mix together, and this is seemingly the origin. And people say that this kind of thought was present in Democritus' thinking. So now, of course, then science developed, and we will make a big jump because I have no time to talk about history of science. This would take weeks and weeks and weeks. Let's jump. Over the years, then scientists, chemists, physicists, and so on, they analyzed this matter around us, and they then discovered that it was indeed made of things they called elements, of pieces they called elements, and they give them names like iron, zinc, lead, and so on. And this seemed a bit complicated, a big bunch of these elements, like a zoo. And it took the 19th century, middle 19th century, to have people make some sense out of it. The person who was most operational in that was a Russian chemist, Dmitry Mendeleev. He brought order into this sort of chaotic picture of all these elements which had been discovered. In 1869, that means just almost a little bit more than 150 years ago, last year it was the 150th anniversary of Mendeleev's paper, which is a landmark paper, here shown here. I show you the original paper in the German journal Zeitschrift für Chemie, and in English, it's on the relationships between the properties and the atomic weight of the elements. Mendeleev had noted that if you consider the properties of the elements and their atomic weights, you could organize them in a table, which is shown here. This is the original table. Here you are looking at the very original table, which was proposed by Mendeleev in this paper of 1869, where you have columns and rows here, as you can see, of elements. And for instance, you can see here this is barium, boron, carbon, nitrogen, oxygen, fluorine. This is, as you can see, this is one of these rows. You have sodium, potassium, rubidium, cesium. That's another one, and so on and so on. So this is a classification of the elements. Mendeleev even introduced question marks, because at that time he was convinced that here these were elements which had not yet been discovered and they must exist. This is being quite courageous to say this must exist. There's a lot of confidence in his organization, in the way of looking at things. And of course, they were discovered. So this is what we now call the periodic table of the elements, and presently it has this aspect. This is the present day periodic table of the elements which make up visible matter. These are the bricks of matter, the visible matter in our universe. Now I like to insist on that, and I always insist quite a long time on this, because this is one of the most important advances in understanding visible matter, in understanding the elements and the universe, in science in general. Why? Because this table shows us the bricks of matter, and there are no other bricks of visible matter in our universe. How can one be so strong in stating that? It's even, I guess, for a scientist, it's very dogmatic. It's you don't feel well, you don't feel so confident, but that is it. This is just because these bricks of matter are like counting 1, 2, 3, 4, 5. There's nothing between 1 and 2, nothing between 2 and 3, nothing between 3 and 4. And here what we do, we just count. You know that atoms are made of a nucleus with protons, neutrons, and of electrons around them. So this is 1 electron, helium is 2 electrons, lithium is 3, 4, 5, 6, 7, 8, 9, 10, and so on. You just count the number of particles making up the atoms. And all matter, all visible matter in our universe is made of these elements. So if there is any living organism, thinking organism anywhere else in our universe, that entity will be built from the same elements. It will be built from carbon, oxygen, nitrogen, maybe some other elements which we don't have to use so much. Maybe it's built of arsenic, maybe it's built of palladium, maybe it's built of yttrium. I don't know, but it is these elements. The natural elements, they go to uranium here. These are artificial elements which are made in accelerators, in big atom smashing machines. But these are the natural ones here up to uranium. And we are made of that. These are our elements. These are the building blocks of visible matter. And this is the playground of chemistry. Chemists are like children. Children, you know, you certainly in Hong Kong have the same. This game, which is called Lego, where children can build large structures on the basis of small building blocks. And this is what chemists do. They are like children using the elements, combining them in infinite shapes, structures, and an infinite possible combinations. Now, this is a structure of matter. What is, or let's say, the composition of matter? But then you have to be able to transform matter, to transform objects in matter from one to another one. The basic law of that was proposed by Lavoisier. It is the basic law of transforming objects, chemical objects, into one another. He said, nothing is lost, rien ne se perd, rien ne se crée, nothing is created, tout se transforme, everything is transformed, is transformable. And this is the basic law of chemical reactions. You have a certain number of elements in your chemical entities, your molecules. They react with one another. They give a reorganization. Other types of entities which are reorganizations of the elements. And this is the basic law, without which, of course, you cannot do any chemistry. Now, we have just now talked about the composition of matter. We have talked about transformation, the laws of transformation, the rule of transformation. But matter is not just a composition of elements. People noted then, also in the middle of the 19th century, that elements can be connected, and they are connected following given rules. There's not anything happening. There are rules for connecting the elements together. So they came up with graphs, graphical representations. You can see here, I showed only 3 of many which had been proposed, and which show ways of representing molecules, combinations of atoms. Wurtz in France proposed the top one. Kekulé in Germany proposed the bottom one. These are, well, they are not wrong, but they are sort of strange representations. Loschmidt in Austria proposed this in the middle, which is much closer in many respects, because he considered a big circle for being a carbon atom, a small circle for being a hydrogen atom, and this is then a representation of 4 molecules. Let me just look at the second one, ethyl alcohol, which you know, that's the alcohol which is very much used by human beings too. And here it is. This ethyl alcohol is CH3CH2OH. So the representation of Loschmidt is quite correct. But of course, complicated molecules cannot be represented graphically by circles. It's much too complicated. So this is now, we now use just symbols, just letters, C, H, O, N, and so on. So now we know that chemical entities are not only composition, they have a connectivity, they have a graphical structure. But is that all? No, it is not all. These graphs are not just something you can write on a piece of paper. They are objects. These are objects which have a structure, which have a sort of a shape, which have a shape. And this was introduced, this notion was introduced again in the 19th century. As you can see, it was very, very fruitful in terms of chemistry. It was, as I already said, a periodic table. It was the chemical formula. And it was the fact that these structures have shapes. These molecules, these objects have shapes. In 1874, 2 chemists independently proposed that chemical objects have a shape. Van 't Hoff in the Netherlands and Nobel in France independently proposed, and they were convinced to be right. They said that chemical objects have a shape, and this was stereochemistry. Before I stop this very, very brief overview of science, of development of chemistry, I also mentioned Pasteur. Pasteur, of course, he was the first who recognized what is called molecular chirality, that molecules can be either like a left hand, as you see here on the left, or a right hand, as you see here, down here on the right. These are molecules which have a chirality, which are not superimposable in their, which are, there's a plane of symmetry here between the two. They are not superimposable, so they are symmetric with respect to a plane. This is molecular chirality. Let me also add something else. What Pasteur also did, of course, is much more than that. He was also one of the proponents of vaccines, and in present times, we are all waiting for a vaccine. The first real experiments were made by Jenner in Britain, Great Britain, and Pasteur had used the vaccine to vaccinate the child and then against the disease. So at that time, we can now say, okay, we have gone from atoms to the molecule, and out of that, molecular chemistry has built up, and molecular chemistry is built on the formation of complex assemblies of atoms linked by very strong connections called covalent bonds, and chemists have then built up molecular chemistry, which is a way to master the organization of molecular matter, the organization of atoms, to connect different atoms together in very complex forms. And we can look at two milestones which illustrate that. The first milestone is the production in the laboratory of urea by Friedrich Wöhler in Germany in 1828. Wöhler made urea from another chemical which is called ammonium cyanate. This was, first of all, what chemists call a synthesis, a generation, a making of a molecule from another one, from another chemical entity. It had, however, at that time, another very important signification. At that time, I was thinking that one could not produce a compound contained in a living organism without the help of a magic force, which was called the vital force. And otherwise, if you wanted to make anything contain a living organism, you had to use this magic vital force. However, Wöhler was made urea, which is contained in urine, that means in a living organism, from ammonium cyanate, which is not part of living matter. So he had just destroyed the notion of vital force. This magic force did not exist. There's a continuity between non-living and living matter. Living matter is just another type of molecule, another type of chemical object. Now let's jump by 150 years or so to vitamin B12. Vitamin B12, we have it in our organism. It's a very important vitamin in our organism, and it has as an important characteristic that it is a very complicated object. It's a very complicated object compared to urea. This was produced in the laboratory from its building blocks by what is called total synthesis. Total synthesis is progressive build-up of the molecule by organizing the atoms, carbon, oxygen, nitrogen, and so on, in space at the right position, at the right in the right structure, the correct structure. And it was done by two groups. One was directed by Robert Burns Woodward at Harvard University in Boston, and the other one by Albert Eschenmoser at ETH, the Polytechnical University in Zurich, in Switzerland. They were, of course, they had a large number of co-workers, and it took about 10 years with, let's say, 120, maybe 150 man and woman years to get this thing done. And it was done, and it was a large construction. It was sort of, to say, the Himalaya, the top achievement of chemical synthesis at that stage. But of course, it was not the end of it, and molecular chemistry continued to develop over the years and to generate more complicated molecules, even much more complicated, new drugs, new materials, discover new reactions, new procedures for processes, for industry, and so on. So molecular chemistry is a very adult science with a strong development, and which will continue so. And at that stage, of course, and it continues nowadays, of course, many people contribute to it in all universities, research groups, industries, companies, and so on. But we have then to ask another question. We think one should. And this question is the following. I illustrate it by taking a biological example. The blue sphere here is a cancer cell. These two purple bodies are two killer cells. Killer cells are the cells in our body which make the police, which try to find out which cells have turned bad, have been transformed into cancer cells. And they have the mission of this to find it and to destroy it. Killer cells should not make a mistake. If they destroy a healthy cell, or if they do not destroy a cancer cell, you have a big problem. So how do the killer cells know that the partner, the one here, the blue thing, is a cancer cell? I can give another example. Here is a cell, a white blood cell with blue dots. These blue dots, this is the HIV virus. And this HIV virus, when it hits a white blood cell, can infect it. How does a virus know that it has reached its goal? In these two cases I illustrated, these objects which come into contact must have information about what the partner is. So for the killer cells to recognize the cancer cell as something also to be destroyed, and the HIV to be the goal, the HIV virus to be the goal, and being able to infect the white blood cell. So what happens? These objects are made of molecules. And these molecules, these are large objects made of many, many molecules and delineated by a membrane. And when they attach to each, when they get into contact, there are molecules on the surface of the cancer cell and molecules on the surface of the killer cells which recognize each other. They feel each other. There's information for the killer cells in the molecules which are on the surface of the cancer cell. This means that there must be a chemistry which is dealing with what happens between molecules, between the molecules at the surface of the cancer cell and molecules at the surface of the killer cells. And that means that beyond molecular chemistry, there must be another chemistry which does not concern what happens inside the molecule, the buildup of this molecule, but the way in which molecules interact with one another. And this is what I have called supramolecular chemistry, which is the way of trying to understand how the interactions between molecules lead to attachment and lead to associations. It is mastering the interactions between molecular entities, non-covalent bonds. And three main functions were studied: how do molecules recognize one another, how can they react with one another, how can they carry one through a barrier like a membrane. I come back to that, transport processes. But the basic one is, of course, molecular recognition. How do molecules recognize themselves? This can be represented in very simple terms. Of course, it's quite a complex process, but it can be at the start represented in simple terms. Molecular recognition first involves interactions. They have to bind together, they have to feel these molecules, each other. If they don't interact, they ignore each other. But another feature, information, must be present. You cannot recognize without having information about the object to be recognized. Therefore, this molecular recognition process is an information process. In its most simple terms, it can be considered to be a complementarity of two features: the geometry of the objects in contact and the way they interact, the interactional features. Now, a very simple representation of this has been given very early on in 1894, again the 19th century, by Emil Fischer, a German chemist who got the doctorate, his doctorate in Strasbourg in 1874. We were very proud of the fact that Emil Fischer got his doctorate in our university. He is the one who wrote in 1894 a very, very famous paper also, which is the basis, let's say, I could say almost the basis of biology and life. He said that for a molecule to act on the other one, they have to fit together like Schloss und Schlüssel, like a lock and a key. And this is represented graphically here. Very simple representation. It is, of course, much more complicated than just fitting two objects, but the basis is really that. The gross picture is fitting together. But of course, we know that the fitting is not just geometrical fitting, it's interactional, it is functional fitting, and so on. But it is the basis. And when I give general public lectures, if you come away from my lecture, you go away from the lecture and just remember that biology is based on locks and keys fitting together. You have already learned a lot of things. Now, the basis of this, let's have a look at it, the most important application of this molecular recognition. This is simply and complex, and of course, simply is a way to present it. It is the molecular storage of information in the double helix of DNA. And the double helix of DNA, as you know, represents the genome of living organism, the genetic program of living organisms on our planet. This genetic information is extremely simple if you consider the complexity of the organisms themselves. It is just made up of a long strand of rather simple chemical entities onto which are attached 4 letters, to which chemists have given a name. This group they call adenine, this group guanine, this group thymine, and this group cytosine. For chemists, these are very simple molecules. But these are the 4 letters A, G, T, C, which write the genome of living organisms. And it's the sequence of these letters which makes up that genome. So the result, what makes a difference between a tomato and an elephant, or between a dog and a human being, is the genome, the sequence of letters, which is the basis of characterization of a given organism. Before I continue, because this is storage of information, but I would like to come back to one letter. Let's look at adenine. Adenine is this here. Even for those who are not chemists, you can recognize that adenine is formed of 5 HCN. HCN, there's an NH, of course, it's a bit rearranged, but if you count, there are here 5 carbons and 5 nitrogens. So it's 5 HCN. And also 5 here, the hydrogens. HCN is a very small molecule. It is found in interstellar space. A combination of 5 of those gives adenine, which means that a simple combination of a very simple small molecule into a quite simple, more complex molecule adenine represents 1 letter of our genetic program. If you add some water, you can make guanine another letter, and you can make cytosine and thymine by some other chemical transformation. So this is a prebiotic, before life existed, self-organization of molecular matter, forming the components of molecules of life. I don't want to go into the proteins, this is more complicated. Now, this is the construction, the build-up of this letter, of this information pieces, these molecular letters. How do you read the information? The molecular reading, the reading of the information comes by pairing up the letters. Adenine can pair up with thymine or uracil, which is a slight modification, by 2 points of interaction represented by these dots. And guanine can pair up with cytosine by 3 points of interaction. So again, it's very simple. It's really, it cannot be simpler. It is a binary system where the reading is done by 2 interactions or 3 interactions. These interactions are supramolecular. They are interactions between molecules, and they are this binary system which allows one molecule to read the other one by this association, this pairing. So it's 2, 3, 2, 3, 2, 3, which is a reading pattern like in a computer, it is 0, 1, 0, 1, 0, 1, which is the way in which you store information in sequences of zeros and ones. Here is sequences of 2s and 3s, 2, 3, 2, 3, 2, 3, 3, 3, 3, 2, 2, 2, 3, and so on and so on. So, if we come back to what chemistry really is, and what we said now, chemistry is an information science. It's an information science where this information is stored into the molecular structures, and it is processed by the contacts between molecules, these recognition processes at the supramolecular level. That means that chemistry is the science of informed matter, not just the science of how matter is built, how is the structure of molecules, but also the information contained in chemical objects. So let's, it's sort of an interesting old picture, which I found, which is in fact quite well known. There's an earlier representation of the double helix. As you can see here, that's the bottom of the picture, where you have a double helix here, here. And what is on top of it is this. This is an old picture, and in some respects, one can comment on it in a very, very interesting fashion. The double helix is the genome of human beings. How do you transmit the genome to your children? Through a man and a woman. You need a woman and a man to transmit the genome. So this is a sort of a very interesting picture where the double helix is the pillar on which then builds this transmission of the genetic information. Now, let me just say a little bit, and I'm often asked, how did we come to these kind of ideas? After returning from my postdoctoral work, when I worked with Robert Woodward on the total synthesis of vitamin B12, we did for a long time more molecular physics and using chemistry to study physical processes. But I was also very interested in trying to contribute in some way to understanding the most complex feature of us as a living organism, which is the brain. Now, the brain in 1966-67, as a chemist, you could wonder, is there any process in the brain or in the neural system, which can be approached in chemical terms in a not too complex fashion? So this neurochemistry, did it offer a possibility for a chemist to contribute? And there's a process which is very well known, which is perhaps a point of access, which is the propagation of the nerve influx. What is it? It is the exchange of sodium and potassium ions across the membrane of a nerve, of the axon of the nerve, and it's the propagation of these changes in sodium potassium, this transfers of sodium potassium between the nerve through the nerve membrane, which makes the propagation of the action potential. Now, sodium potassium is the clue here. And this is something a chemist understands very well. What is sodium potassium? So one could surmise that in these membranes of the neurons of the axon, these membranes here, there must be molecules able to make the difference between a sodium ion and a potassium ion. There must be selective binding and selective transport of sodium and potassium ions across the membrane. Sodium, potassium, this is something chemists can handle, and so the basis of it was, how can one understand that? Now, sodium and potassium are part of one column of the periodic table of lithium, sodium, potassium, rubidium, cesium. This is one column of the table. In this column, there are these two, sodium and potassium. So it's a collection of 5 spherical objects, 5 atoms, which when they lose a electron become 5 cations, 5 entities of increasing size and bearing one positive charge. So the question is, how can we distinguish between that? How can we selectively bind and transport the spherical cations? How can we therefore perform molecular recognition? Chemistry has this power of asking a question and testing it. The test here was to say, all right, we have a collection of spheres of different size. These are the keys. Let's make the locks for recognizing these objects. And this led to from this generation in the laboratory of molecules, which we call cryptans, because they have a crypt, have a cavity inside, which you can chemically make larger or smaller, and where you can adjust the central cavity to the size of a sphere to get in. The first one is selective, fits well for lithium. This one fits well for sodium, and the third one on the right fits well for potassium. The cryptans are these molecules, and when the cavity is full, has picked up the substrate, and we call it the cryptates. Let me just indicate that this work was done by two collaborators in 67, 68, 69, and until 70, 72. Two collaborators, Dr. Bernard Dietrich and Dr. Jean-Pierre Sauvage. And Jean-Pierre Sauvage received the Nobel Prize in Chemistry in 2016, just 3 years ago, for work in molecular machines. Now, let me also point out that chemists also like the aesthetics of their objects. This is just another representation of this cryptate, which is an organic molecule, and inside the cavity is this metal cation. And a friend of mine, a chemist from Hungary, at the University of Veszprém in Hungary, in Central Europe, made this sculpture where you have the cryptand surrounding the cryptate. It's a rather nice sculpture. I like it very much. He was a very inventive chemist who became a sculptor, and he produced many other such sculptures. I show you 4 more, and I want just to illustrate this one on the right. You see, this is called the scent of the rose. The scent of the rose is the dominant scent. Of course, roses, depending on what they are, on the type of rose, smell differently. But let me just tell you about this main component, which is called phenyl ethyl alcohol. And this is phenyl ethyl alcohol. Here's the phenyl ring, CH2, CH2, OH. So this is a very nice artistic way of giving a shape to phenyl ethyl alcohol. Just to show you that molecules have aesthetics too. So molecular recognition, as I said, this is very important. I try to illustrate that. And I just want to make clear that, of course, one can then make things more complicated. One can design receptor molecules for different keys, receptors for substrates, and then to obtain their supramolecular entities very selectively. So there were very many studies have been conducted in numerous laboratories everywhere around the world, many also, of course, in Hong Kong, in mainland China, in Japan, in many other, many countries, in almost many laboratories. And this developed very well. So now, let me just come back then to where we are. In 1828, molecular chemistry was introduced by the work of Friedrich Wöhler on the synthesis of urea. This led then to the possibility of developing molecular synthesis and generating molecules which can recognize others. And in 1978, I proposed the name of supramolecular chemistry for the chemistry which deals with the interaction between molecules, a receptor with a substrate, and these interactions leading to the formation of a supramolecule, which have specific features, molecular recognition, transformation or reactivity, translocation or transport, giving functional supramolecular systems. So that's more or less the picture, where then many studies were performed for trying to understand molecular recognition, trying to understand and control reactions and transport processes. At this stage, I want just to shift a little bit to also speaking about some applications. As you know, basic research is acquiring knowledge. And applied research is then applying that knowledge. Of course, both are very important. And for somebody who acquires knowledge, it's always extremely satisfying that this knowledge is applied. And for applied research, it is welcome to have new knowledge to apply. So the first characteristic of this application is that molecular recognition is the basic process by which drug discovery can be performed. Let me just, very simple terms, say that a drug is a molecular key for a biological lock. It is supposed to influence the biological lock, either to inhibit some function or to amplify some function. So molecular recognition is the basis of drug discovery, of drug activity, of drug design. And we studied one, but I don't want to get into details. Then one can also make, of course, a variety of these objects. And here I just show you another one, which is here a molecule, which is a different, is still a crypt, sort of a crypt, but of different structure, into which one has introduced an element of the periodic table called europium. And when these two are put together, if you shine UV light on the external skin, it emits red light. This can then be used as a label for medical diagnostics for an immunoanalysis system, which was used to develop this apparatus, which is used in many hospitals for medical diagnostics. The whole process was developed by Gérard Matisse at a French company called CityU. Now, I also mentioned very briefly, I just said that it existed, transport processes. Transport processes are these processes which make possible in the nervous system, the way I started with, this transport of sodium and potassium through a nerve membrane. Now, it also became important more recently as gene transfer. Indeed, gene transfer is a transport process where you want to introduce a piece of DNA, a gene, into a cell by helping it to cross the cell membrane, go to the nucleus, come to the RNA, then make the protein product of this gene. For that, one can use either a processes using viruses, that's not our game, but also synthetic vectors can be designed to envelope, to go around, to envelope the DNA and then help it to cross the membrane. And this is, of course, the development of important agents, artificial agents for gene transfer. These gene transfer agents are of importance for biotechnology and for gene therapy. For the moment, one has used them, and they are mostly, for the moment, objects of research, but these gene transfer agents are very important. I would also like to insist on one thing. They allow this, or let's say in general, gene transfer is a technology which is very powerful and we must use. It's a way to make genetically modified organisms. I like usually to insist on that. Nowadays, people are afraid of gene transfer. People say genetically modified organisms are dangerous. That is not true. We control very well how to do gene transfer. The gene transfer and making genetically modified organisms will help a lot mankind, for instance, in agriculture, to make plants which will resist drought, which will be able to grow in conditions where there is less water, or in conditions where it's much warmer than it is nowadays. So I think genetically modified organisms you have to think about as a scientific advance, a very important scientific advance. Biomaterials are also another outcome of this supramolecular chemistry, making supramolecular polymers, which can be biocompatible and biodegradable materials. I illustrate that in the following way. As you can see here, supramolecular materials have been developed as biomaterials, biocompatible polymers, and they were applied for making cardiovascular implants, for correcting, for reconstructing the heart of children having severe cardiac malformations. This is something which happened, you see. We introduced the concept of supramolecular polymers in 1990. In 2013, it took 23 years to be applied because, indeed, between a basic research process, which opens a field, until applications can be done, and especially applications for introduction into human being, it takes a long time because of all the developments which have to be done in the between one and the other. And it was done, and here is the first little girl who was implanted on the October 23rd, 2013, Dominica. She was operated on by Professor Leopoldo, who is a cardiovascular surgeon at the Pediatric Center for Cardiovascular Surgery in Moscow. And you see that both, this is 3 months after implantation, and they are both very happy. She is happy and he is happy. It worked, and she is still in good shape. This is now, this was in 2013, so it's 7 years later. Now a lot of children have been treated, and the same company has also developed now heart implants, pulmonary heart valves, which have been tested in Budapest, in Krakow, and Kuala Lumpur. Supramolecular polymers are also materials which have a property of being self-healing. Let me just illustrate that without going into details. By this very nice film, transparent film, you can see it's almost ideal in terms of transparency and lack of deformation. You cut it in 2 pieces, you superimpose the 2 pieces here, you press with your finger for a few minutes, and you can stretch and it sticks. In other words, the cutting has been healed, and the film is again a continuous film, a film which can be considered as having healed. Now, let me go back to the main theme just for a short time. When you understand better how molecular recognition operates, you can try to use this to set up in the laboratory systems undergoing self-organization, which means that you want to use molecular recognition patterns, the way in which entities recognize, to generate supramolecular complex architectures in a spontaneous way, but in a controlled fashion. An example of that is the buildup of a virus. And I here take the simplest one, the tobacco mosaic virus. It's a simple virus. It is composed of 2,130 bricks, which are protein subunits, which are represented, you can say, more and more complex, the piece of cake here, or this unit here, or this unit even more detailed. And these pieces can go together spontaneously and build up due to their shape and the way in which the pieces interact with one another to build up the tower, helical tower, into which fits the RNA, the genome of the virus. Now, this process is a spontaneous one. It happens spontaneously when these objects are in presence, and it generates automatically by self-organization the tobacco mosaic virus. It looks like magic. It is not magic. It is basic chemical processes involving structural chemistry, involving organic chemistry, biophysical chemistry, physical chemistry, and so on. So it is no magic. It's a basic operation, a basic process which is just due to the fact that the subunits, the pieces, have the right shape and the right interactions. And this looks like a sort of a programmed chemical system into which you introduce a molecular program. The information is stored in the components, and the supramolecular operation processes the interaction pattern via the specific pattern, which may be considered as a sort of a recognition algorithm. So can one do that in the laboratory? Of course. Such processes are the basis of living organisms. I have shown the very simplest one of a virus, which is not even living, because as you may know, even including COVID-19, this is just a bunch of molecules. It's a stupid bunch of molecules, which doesn't live. It's just molecules which have given recognition processes, and it's these recognition processes which gives them their properties. Now, if we want to see if we can do similar things in the laboratory and build up self-organization procedures, let me just give you an examples coming from one area, which is to use bricks components which are able to bind metal ions and connections which are the metal ions in question. In other words, you have bricks made up, molecular bricks, and they are brought together by interaction, by sort of a glue, which is metal cations. Many of them have been made. I showed you some examples from our work. I have shown you the double helix of DNA. One can make artificial double helices, which have absolutely nothing to do with DNA, except that they are double helix or helical. Here on the right-hand side, you see a double helix, which is organized from two molecules. They are colored artificially, of course, into two different colors. And you don't see here the metal ions, they are hidden behind the molecules. Here it's a bit easier to see. That's a triple helix, 3 strands wrapping helically around each other and held together here, these yellow points, by 3 metal ions and giving them a helical shape. So that's, again, a spontaneous formation on the basis of the way the ligands, the strands, are built and the metal ion which brings them together. That's an example of what you may call a nanocylinder, a nanocontainer, where 3 linear molecules in red, 4 flat molecules in blue, and 12 connectors which link everything together, and they build up also spontaneously from 19 components which go together to generate this specific nanocontainer with 3 cavities. 3 linear molecules, 4 planar, 12 connectors, altogether 19 components which go together to generate this nanocylinder. There are some others, just to show you that, okay, there are interesting things to be done. There are nice molecules of all types. And these are now rather simple ones compared to what is achieved now in the people working in these areas, where they can make more and more complex molecules for more and more complex procedures and features and functions. So this is also of interest to sort of expand on it. For nanoscience and nanotechnology, indeed, as you know, for the moment, we make devices, computing devices, computers and other information processing devices by fabricating the device and then manipulating them, putting them into the right organization. Now, if self-organization can be used, it would mean that one would like to generate supramolecular architectures, these complicated assemblies, spontaneously by the possibility to organize the objects through recognition between the building blocks. This would be a self-fabrication. Rather than having to make the object, to make the device, it is to let it make itself. And of course, that may be considered as an ultimate form of fabrication. It would mean being able to design components which simply by interacting with one another can lead to the organized device. In the future, that can be maybe not an alternative, but an important complement to the present procedures. Now, just one word about what is going on right now and what we are working on. I have insisted up to now by chemistry by design, where you try to implement information, programmation to store information into molecules and let it perform its job. And this leads then to, as we just saw, controlled generation of molecular and supramolecular entities, controlled, spontaneous, but controlled. Now, one step further into complexity is to let the system choose what it needs. In other words, it's selection. Let the chemical system choose the pieces it needs to build itself up. And this involves diversity. We need different building blocks to do that, and dynamics. You need a way in which these can exchange, feed each other, dissociate, associate, and so on. And this then leads to a chemistry, which is now a new type of chemistry. Not so new, it's already 10, 12, 15 years old, but it is quite recent compared to supramolecular chemistry, which is now 50 years old. And it is a chemistry which bears on the possibility for a chemical object to change its constitution by dissociating into its components and reassociating into a new structure, or it may be the same structure or another structure. And this then makes possible a change in structure on reconstitution if the conditions have changed, and adaptation to a change in constitution, that is adaptive chemistry. In other words, if I summarize, the chemical object is made dynamic in its constitution. It can fall apart and recombine, and this can happen differently if the conditions have changed. So the system may respond to external agents and therefore adapt to these changes. And this is a way to develop what we call adaptive chemistry. So this adaptive chemistry is then a case of interest. Let me just very simply sort of summarize. This adaptation through variation in constitution can lead to new ways, new procedures for searching for biologically active substances. This has been done for dynamic nanostructures, for nanoscience and nanotechnology, and also dynamic materials, which can lead then to properties which static materials do not possess. So far, let me just come to a sort of a summary before I go to some more general considerations. Molecular chemistry is the basis, which are the bricks of matter. The elements are the bricks of matter, and this next step is the molecules, which are the combination of elements. Then the molecules themselves can combine into supramolecular chemistry. They can get organized, then dynamic, then adaptive, and of course, beyond that, maybe evolutive and so on. But these are steps in which chemistry has evolved and becomes more and more complex towards living matter, and of course, eventually, ultimately, towards thinking matter. Let me now just finish with some general considerations. As you may have known, may have seen, I didn't speak so much about, I spoke a lot about using terms like living, thinking, and so on, but I didn't give many examples of it. I showed you many examples of objects, chemical objects, which were not biological ones, which means that in fact, the chemistry is not just to discover what already exists, like the components of living organisms, but also to create objects, chemical entities which do not yet exist. That means that we have to write the book of chemistry, not just to read it. It means that we have to compose the score of chemistry, not just to play it. It indicates that chemistry has a creative power like art, and that is why I like also to illustrate it by another sculpture of Auguste Rodin The hand of the artist expresses out of a stone a sculpture here, which is not contained in the stone. It's the hand of the artist which does it, which brings it out, which shapes the stone. And that's the way in which chemistry in particular and science in general shapes matter. Chemistry can be considered as the art of matter. It is making out of elements all these objects, creating all these objects which are not yet known, have not yet been created. This type of consideration can already be sort of deduced, can also already be found in here 500 years ago. I did one more year again. Last year was a 500th anniversary of the death of Leonardo da Vinci. You know Leonardo da Vinci, I suppose, probably all of you. He is an artist, you know Gioconda. He is a scientist and he's an engineer. So this person has written a sentence which is very, very strong. Where nature finishes to produce its own species, we are part of that. Man begins using natural things. These are the elements of matter, the periodic table, if you wish, in harmony with its very nature. These are the basic laws which regulate the way in which these natural things can form. But the ending is very strong, especially for somebody who combines being an artist, a scientist, and an engineer to create an infinity of species. Meaning to create, to make all these entities which are an infinite number, which do not yet exist and which we can make. Of course, there are many, many, many which exist and which we have to learn about, but there are also many, many which we can make, like a painting, like a piece of music. There are many, many, many you can paint with the same colors, many, many, many pieces of music you can write with the same notes. Now, going back to this, I hope this Chinese here, this was done by one of my collaborators, I hope it's correct. In the same country of Greece, there was Prometheus, who stole the fire of knowledge from the gods. And he wanted to bring it to mankind, and here he's running away, looking over his shoulder to see if the other gods are not trying to catch him. They were not able to catch him, and here he is, Prometheus, holding in his hand the fire of knowledge given to mankind. One major consideration is we acquire knowledge, but we cannot give it back. The knowledge we have is there to stay. You cannot erase it, and we have to live with it. Knowledge is understanding what is around us, what we are, what we will be, probably, but this we cannot erase. What you know, you know. So our path of us as human beings on our planet, but I say again, there may be on other planets, other entities working along similar lines. Our path leads us from the quest of knowledge, looking for knowledge, to control of our destiny. This gives us, this knowledge, the possibility that we control our own destiny. For the audience, there are many of you who will someday hopefully become scientists. Science is an activity where you have to be bold, to look out, to look for new things, new understanding, new knowledge. And as this Chinese poet said, If you sit at the bottom of a well to contemplate the sky, you will find it small. You have to stick your head out and look at how big, how bright, how wide the sky is. In the past, information transfer went through one entity, one species, like here an ape, and a human being. Presently, information transfer can occur through human beings. In the future, maybe that's a way to shake hands and to transfer information, recognition, and all that. I don't mean by this that we will shake hands with only robots. There may be some, why not? After all, I mean, if it's just a machine, we can shake hands with it, if it is designed for that. However, what I want to show by this is that we will no doubt transform ourselves. In fact, we have already transformed ourselves. For instance, we may have new teeth, which are not our natural initial teeth. We may have in our eye a new lens to replace the natural one, which didn't work anymore, which had become opaque. Furthermore, I can even push this a bit further. If I get a heart transplant from another person, I cannot tell my wife, I give you my heart. It is not my heart anymore. It is the heart from another person. And in the future will probably be a heart which has been engineered by understanding the mechanisms of development from stem cells. So what I mean is that understanding living organisms, we will be able to do so. We will be able to use this understanding to change ourselves. The question is how? What do we want to do? Let me finish by citing a mathematician. I have not said a lot about mathematics. Here is a very famous mathematician, David Hilbert, who is buried in this small university city in Germany, Göttingen. And he has on his tombstone, he wanted to have written two sentences, one here and one here. One here, one here, these two sentences. What do they say? Very interesting. The top, wir müssen wissen, we must know. This is already a very strong statement. Huh? That's a statement for us scientists. We must know. We don't want to walk around not knowing, not being able to understand. We must know. But the second part is even much stronger. It's a sort of a vote of confidence. Wir werden wissen, we will know. It's a vote of confidence that we must know, yes, and we will know. Now, how far it will go and so on, the future will tell us. But here is what drives scientists. Scientists are driven by the fact that we must know, and then we will know, thanks to science. I understand that many in the audience are high school students. You are at the beginning of your life. You have to be very conscious of the fact that mankind needs more science. Mankind needs to be scientifically more educated. Mankind needs to spend time on trying to understand science, not necessarily in all its details. There are the people, the scientists who do the science, but the general mankind, the general people in the general public have to know something about science. And as I often say, people are ready to spend hours a week to learn tennis, playing tennis, for instance. Why don't they spend a few hours learning science. Okay, why not play tennis? But more important would be to learn some science. So I say to you, young people, science shapes the future of humanity. Participate. We hope you will participate, because through science, you will shape also, using science, the future of humanity. Thank you very much. It was my pleasure to be with you.